Okay, let's get started. Let me take over first. Alejo Legares, Adrian, Alejo Legares just not here. Me, here. Francois, Woods,
Here.
Himes,
Here.
Hodges is here. David,
Here.
Lee,
Here.
Momberg is here. Martin,
Here.
Medina, Moreno, Medina is here actually. Moreno is here. Perouche, Simmons, Wheeler,
Here.
White, and Zaragoza.
Here.
All right, so we are going to continue and complete chapter 4, which, and if I remember correctly, the last time we were here, we started talking about redox reactions. And what we're going to get into today to complete this chapter is how do we go about balancing equations for these reactions. And you're going to see that things are a bit different when it comes to balancing equations for redox reaction. Now, before we get to that, I want to remind you of something where we left off the last time, I think. And please tell me if I'm wrong, but this is the example of a redox reaction that I mentioned earlier. And the equation for this reaction is Mg plus Mg plus CuSO4 to give Mg, what is this? To give Mg SO4 plus copper, right? And I remember saying that we can split this into two half equations, and the net analytic equation would be Mg to form Mg2 plus 2 electrons, and Cu2 plus 2 electrons to give Cu, right? These are two half equations for the reaction, for the overall reaction. And one key thing I want to stress here before we actually move on to balancing equations is that whenever the number of electrons lost in the oxidation, this is oxidation, right? Whatever the number of electrons lost in the oxidation half reaction must be equal to the number of electrons gained in the reduction half reaction, right? That is true for every single redox reaction. Number of electrons lost must be equal to the number of electrons gained, right? So that's something important I thought I should stress here before we move on to balancing redox equation. Now, speaking of balancing redox equation, you could actually go out of your way to try to balance these equations in the way that you would have learned from your high school or introductory chemistry. But what you'll find if you try that traditional approach is that it becomes very difficult, right? And therefore there's another method that is used, which is more friendly in terms of the length of time that it would take to balance such reaction, right? Now, the best way to learn this, of course, is to go directly to an example. So the example we're going to use is this reaction right here, the oxidation of Fe2 plus to Fe3 plus by the dichromate ion in an acid solution. Now, let me just say that to be fair to you guys, I should also mention, or what should be mentioned in addition to the information right here, is that another product would be the chromium 3 plus ion. So I'm just going to put that here. Cr3 plus is also a product. All right. You guys wouldn't have known that So that's why I'm introducing that there, right? Okay, so let's say you're given that information and you're asked to balance the equation representing that reaction, right? In order for you to do that, of course, you have to figure out what would be the reactants based on information provided and what would be the product, right? So basically, this is the setup for the unbalanced equation. Based on information provided, the Fe2 plus and the Cr2O72 minus, that's called the dichromate ion. These two are the reactants, and the Fe3 plus and the chromium 3 plus would be the products of this reaction, right? Okay, so that's the first step in balancing a redox equation. You have to write down the unbalanced equation, which means you have to figure out what the reactants are and what the products are, right? Okay, the next step is that you separate this equation into two half equations, right? One half equation would be the oxidation and the other half equation would be the reduction. So in the case of the oxidation half equation, that would be the Fe2 plus going to the Fe3 plus, right? That would be the oxidation half equation. And the reduction half equation would simply be the dichromate ion to form the chromium 3 plus ion, right? So that's the next step. That's step number 2. You separate the equation, your original equation that you have, into two half equations. One half equation would represent oxidation, and the other half equation would represent reduction. All right? Okay, the third step is where we balance the oxygens and the hydrogens. All right, and in fact, I should have modified this to do the oxygens first and then the hydrogens, because that would be 2 steps. Anyway, so basically the next step is that we balance the oxygens first, right? Now the question is, how do we balance oxygens? We balance oxygens by adding water molecules to the side which is deficient of oxygens, and we add enough water molecules to that side until we end up with a balance of the oxygens. So what does that mean? In the case of the first half equation, which is this right here, right? There are no oxygens there, so therefore we don't need to balance any oxygens. But in the case of the second half equation, we have 7 oxygen atoms on the left side, and we have no oxygens on the right side, right? So what does that mean? That means we need to add 7 water molecules to the right. So that by doing that, we now balance oxygen. We have 7 oxygens on the right, which balances with the 7 oxygens on the left, right? So the next step, smell something burning. Smell something burning? Okay, maybe it's just me. Okay, next step, we need to balance the hydrogens, right? Now, how do we balance the hydrogens? We balance the hydrogens by adding H plus ions to the side, which is deficient of hydrogens. And we add it up until the hydrogens are balanced, right? Again, in the case of the first equation, there are no hydrogens, so we don't need to balance any hydrogen in that case. However, in the second half equation, you'll notice that we have 14 hydrogen atoms here. 7 times 2, right? So that means that we need to add 14 hydrogen ions on the left side to balance with the 14 hydrogen atoms on the right side, right? So that's how we balance the hydrogens. We balance the hydrogens by adding H plus ions, right? To the side which has the lower number of hydrogens, okay? All right, so basically as a result of that, I'm sorry. Okay, so what I just described is right here, all right? So basically, we have the 14 hydrogens here, 14 hydrogens here, we have 7 oxygens here, we have 7 oxygens. So the hydrogens and the oxygens are now balanced, right? The next step is, we have a question?
Oh, no. We're just trying to read that.
Oh, it's not here, yeah, you know what, let me see if I can, okay, I'm sorry, folks, I'm not sure how I can, oh, wait a minute. Cool. Okay, I have to go back and make changes here. So basically, Let me write down for the sake of clarity. Right, this would be 14H plus. It's basically what I wrote on the previous slide. 14H plus CR2O72 minus to give 2CR3 plus 7H2. That's basically what that is, right? So basically what we have done in obtaining this equation is balance the hydrogens, the oxygens, and that's it. And I just remembered something. I forgot one important step, which was earlier. I apologize for this. Let me go back to this right here. Very important step to balance the atoms other than oxygen and hydrogen in each half reaction. In this case here, we have 2 chromiums here, we have 1 here. So we need to add a 2 there to balance the chromium. That you should do that first before you balance the oxygen and hydrogen. So I apologize for that, right? So this is basically what you end up with when you do that, and then you balance the oxygens, right? And then you balance the hydrogens, and you end up with this equation like this, right? Okay, the next step is that you balance the charges. And let me just warn you that this is where most students tend to screw up the process, right? Now, to balance the charges, right? In the case of the first equation, we never had this before, right? We had Fe2 plus going to Fe3 plus. So to balance the charges, according to the instructions here, we basically to balance the charges, let me take that out for the time being. To balance the charges, we look at the total number of charges on either side, right? And basically we add electrons to one side so as to achieve the balance. So in this case here, we have +2 total charge. On the right side, we have +3. So in this case here, what we do is that we add an electron to the right side of the equation, right? And by so doing, we are adding a negative charge. So when we add a minus charge to this side, +3 minus 1 will give you +2, which balances with the +2 on that side, right? So basically, you add electrons to the side with the higher net charge in order to achieve the balance. And you add enough electrons until that side's total charge will be equal to the other side's total charge. And we do that to both half equations. So the next half equation is this right here. Let me erase this here. Right? And let me show you how we know that we need to add 6 electrons. So let me just cross this out for the time being. So basically, what we do before we add the electrons, we count out the total number of charges on both sides. Based on this equation here, we have 14 plus charges minus 2. So the total charge on the left side would be 12. And then on the right side, we have 2 times +3, which will be +6. The water does not contribute any charges, so therefore we're going to have +6 on this side. So we have +12 on this side, we have +6 on this side. According to the rules, the next step is to add electrons to the side with the higher net charge, right? Which would be the left side, which has +12. So what's the number of electrons you would add? You would add 6 electrons. So let me erase this now. You would add 6 electrons, right? And the reason why you would add 6 electrons, is because each electron carries a negative charge. So when you add 6 electrons, you're adding a total of -6 on this side. 12 minus 6 gives you +6, which balances with the +6 on the other side. All right. So now we have balanced all the atoms. We have balanced the iron, the chromium, the hydrogen, and the oxygen. So what's the next step? This first. The next step is that we have to ensure that the total number of electrons lost in the oxidation is equal to the total number of electrons gained in the reduction. If you remember the example I gave before, that's what I said. We need to do the same thing for balancing this equation. Now, as we have it right here, we have 1 electron here being lost in the oxidation process, but we have 6 here being gained in the reduction. So the question is, how do we get the number of electrons gained here to be equal to the number of electrons lost here? And the answer is that we multiply this equation here by 6. All right? Because we want 6 electrons here to balance with the 6 electrons here, but that means you have to multiply the other items as well, Fe2 plus and the Fe3 plus, right? So when you multiply this by 6, you're going to end up with this here, right? 6 Fe2 plus to form 6 Fe3 plus 6 electrons. So now we have the number of electrons lost and gained being the same, right? Okay, the next step is we add this equation to this equation. And when we do that, we cancel out the common items on both sides, right? In this particular case, the common items would be the electrons, because you have 6 electrons being lost here, 6 electrons being gained here, right? So when you add these two equations together, the 6 electrons will cancel out on both sides, all right? And that is true for every redox equation, right? The electrons that are lost will be canceled out by the electrons that are gained, right? And then there's nothing else to cancel out in this case. So what do? You write down the result of adding these two equations, which would be this right here, which would be the final answer, or should be the final answer, all right? Now, what I strongly suggest that you do, I suggest this to all my students when they're doing this type of problem, is that you check to make sure that the final equation is balanced, right? So you check to make sure that all the atoms are equal on both sides for each element, and you check to make sure also that the charges are equal as well. Total charges on the left must be equal to the total charges on the right. So let's check that to make sure. Let's start off with the hydrogen. We have 14 hydrogens here, and we have 7 times 2, 14 hydrogens there. So the hydrogens are balanced, right? We have 2 chromiums here. We have 2 chromiums here. So the chromiums are balanced, right? We have 7 oxygens here, and we have 7 oxygens here. So the oxygens are balanced. And then we have 6 ions here, 6 ions here. So the ions are balanced. Then we have to make sure the charges are balanced, right? So let's look at the total charges on the left side here. We have plus 14, because of the 14 plus charges here. We have minus 2, right? Because of the minus 2 here. And here we have 6 times plus 12, which is 6 times plus 2, which is plus 12. Right? So 14 minus 2, make sure I'm saying the right thing. 14 minus 2 would be 12. 12 plus 12 gives you 24 electrons, right? Or 24 charges, plus 24, right? Then we look at the right side. We have 6 times 3 plus 18. And we have 2 times plus 3 plus 6. 18 plus 6 plus 24. So the charges are the same total on both sides, right? So now we can say safely that this equation is balanced, all right? And that's basically how you balance a redox equation, all right? Any questions? Any questions? Any questions out there in Zoom? Okay, what I'm going to do is a couple more examples. So let me get out of this here and go to Word. And I'm just going to make up an example. I don't even know what the answer is going to be, but I think it's important that you understand the process. So let me go here. Okay. So let's say you're given Mn O4 minus plus Cr3 plus to give Mn2 plus CrO4 2 minus. Okay, so let's say you're given that and you're asked to balance the equation. So what's the first step? You separate the equation into 2 half equations. So let me ask you, what do you think the half equations will be when you separate this into 2 half equations? One of them would be what?
the MnO4 with
MnO4 minus to give
the Mn,
Mn2 plus, okay, very good. And then the other half equation is
the Cr3 plus
Mhm.
to the CrO4.
2 minus.
Yeah.
Okay, very good. Right, that's the first step, right? First step is that you separate this equation into two half equations, right? The next step is where you make sure that the number of atoms of all elements excepting oxygen and hydrogen are balanced, right? That's the step I skipped over earlier, which I went back to, all right? So this step is where you look at all elements excepting oxygen and hydrogen and you make sure they're balanced, right? So that would mean that in the case of manganese, that's already balanced because you have one on each side in the case of the first half equation. And also in the case of chromium, same thing. You have one chromium here, one chromium here. So those atoms are balanced, right? So you have to check to make sure that is balanced first, right? The next step is that we balance the oxygens by adding water to the side, which has a lower number of oxygen atoms, right? So let's see. In the case of the first half equation, to which side would you add the water molecules and how many water molecules would you add to balance the oxygens? To which side would you add the water molecules and how many water molecules would you add in order to balance the oxygens?
You would add 4 water molecules to the Mn2 plus.
On the left, on the right side.
Yeah.
Exactly. Very good, right? So you add 4 water molecules on the right side so that the 4 oxygens here would balance with the 4 oxygens on this side. Okay. What about the second half equation? To which side would you add water molecules and how many water molecules would you add?
Be someone that you had 4 water molecules to hold up.
Exactly. 4 water molecules will be added to the left so that the 4 oxygens here will balance with the 4 oxygens here. Okay, very good. The next step is that we balance the hydrogens. And remember, to balance the hydrogens, we add H plus to the side, which has the lower number of hydrogens. And we add enough so that you achieve that balance. So with that said, for the first half equation, to which side would you add hydrogen ions and how many would you add? To which side would you add your hydrogen ions and how many will you add?
8 to the left.
I'm sorry?
You have 8 nitrogen to the left.
8 hydrogen ions. And remember, it's hydrogen ions, not just hydrogens, right? To the left, correct. Okay, so that these 8 will balance with these 8 right here. What about the second half equation? To which side would you add hydrogen ions and how many will you add?
Right side 8.
Right side, how many?
8.
8 hydrogen ions. Very good. All right. So we have balanced all the atoms. So at this stage, what we need to do now is to balance the charges. And remember, you have to be careful, right? Again, students always mess this up, especially when they're meeting this for the first time. So how do we balance the charges? We balance the charges by adding electrons to the side with the higher net charge, right? And we add enough electrons until the net charge of one side is brought down to be equal to the net charge on the other side, right? So the first thing you have to do in order to figure out which side you add electrons is how many total charges you have on both sides. So let's start off with the first half equation. What's the total net charge on the left side of the first half equation? What's the total net charge on the left side for the first half equation?
7 12.
Plus 7, exactly. Because you have 8 plus charges here, minus 1, right? So that's plus 7. What about the right side? What's the total net charge on the right side of the same half equation?
2.
Plus 2 or 2 plus, yeah. All right. Okay, so we have plus 7 on the left side, plus 2 on the right side. So the question now becomes, to which side would you add electrons? Would you add it to the left side or would you add it to the right side?
Right.
To the left side, exactly. And then the next question is, how many electrons? Because remember, you want to achieve equality of charges on both sides. So, exactly, you're going to add 5 electrons to the left side, because by adding 5 electrons, you're reducing the total charge on that side by 5, that gives you +2, which balances with the +2 on the right side. All right? Okay. Any question about that before we move on? Because it's very important that you understand to which side you add electrons and how many. Right? In this case, you add 5 because one side has +7, the other side has +2, right? So you want to reduce the 7 to 2. That means you add 5 electrons. 7 minus 5 give you +2. All right, very good. So let's see if you can tell me about the second half equation. What's the total net charge on the left side of the second half equation? What's the total net charge on the left side of the second half equation? +3, right? What's the total net charge on the right side of the equation? Same half equation. +6 because they have 8 plus minus 2, so that's +6. So +3 on the left, +6 on the right. To which side would you add electrons and how many?
3 to the right.
I have 3 electrons to the right, because by doing that, you're reducing this by 3. That gives you +3 on this side, which balances with a +3 on that side. All right, so very good. So let me clear this here because the next step is to ensure that the number of electrons lost and gained are the same, right? Because that is true for every redox reaction. Whatever the number of electrons lost in the oxidation must be equal to the number of electrons gained in the reduction. Here we have 5 electrons here and 3 electrons here. So how do you propose that we get the number of electrons gained in the reduction equal to the number of electrons lost in the oxidation? How do we get the number of electrons here be equal to the number of electrons here?
You multiply the top reaction by 3 and then multiply the bottom reaction by 5.
Exactly. So, and the reason why you do that is because if you multiply this by 3, you're going to get 15 electrons here. And if you multiply the number of electrons here by 5, you're going to get 15, and therefore they're equal. But remember, you're going to multiply the entire equation by that number, right? So in the case of the first half equation, we're going to multiply this by 3,
I
right?
think that's. I could be wrong, I'm thinking of something like curve operations, I think, but I think that might be the wrong name.
The one that comes to my mind from math is you multiply both by what's curve?
The least common
It's not,
factor.
Something like that, yeah, right.
I just remember like one thing you could do is to have. Like a way of canceling out certain terms.
Right.
You multiply.
Right, exactly right. Yeah, I'm quite sure there's some math principle involved. Which is, you know, almost always true when it comes to other sets. So if I multiply this by 3, what am I going to end up with? I'm going to end up with 15 electrons plus 24 hydrogen ions plus 3 permanganate ions on the left side, and then on the right side, I'm going to have 3 manganese 2+ ions plus 12 water molecules. All right, so that's the result of multiplying the first equation entirely by 3. Okay, so the next equation, as he correctly said, you're going to multiply by 5. So when you do that, you're going to end up with 20 water molecules plus 5 Cr3+. And then on the right side, you're going to end up with 5 CrO4, 2 minus, plus 5 H40 hydrogen ions, plus 15 electrons. All right? So that's what you get when you multiply the second equation by 5. Let me just check to make sure I'm doing the right thing. That's 20, that's 5, that's 5, 5 H40, 5 H50. Okay, so that's what you end up with, right? The next step is where we add both of these equations together. And in doing so, you have to ensure that you cancel out common items on both sides of the equation. So let's do that. What that means automatically, and this is true again for every redox reaction, the number of electrons gained must be equal to the number of electrons lost. So those two will cancel out, right? But there's some other things that will cancel out as well. For example, you see these 12 water molecules here? They will cancel out 12 of these water molecules, leaving behind 8. Want to see that? Right? these 12 water molecules will cancel out 12 of the 20 water molecules here, leaving behind 8. And these 24 hydrogen ions will cancel out 24 of the 40. So 40 minus 24 gives you what? Is that 26? Or 16? I'm sorry, 16. All right. And I don't think there's anything left to cancel out. So what do? We write down what is left, right? So 8 H2O plus 5 Cr 3 plus 3 MnO4 minus, and then on the right side 3 Mn2 plus 5 CrO4 2 minus plus 16 H plus, and that should be the final answer. All right. But again, as I said before, you need to check to make sure that your final answer is correct by ensuring that everything is balanced, right? So let's do that now. Starting with the hydrogens. We have 8 times 2, 16 hydrogens, right? And that balances with the 16 hydrogens on the right side, okay? We have 8 times 1 oxygen plus 3 4 12. So that's 12 oxygens plus 8, that's 20 oxygens on the left side. And then on the right side, what do we have? 5 times 4, 20 oxygens. So the oxygens are balanced, right? Then we have 5 chromiums, 5 chromiums, so the chromiums are balanced. We have 3 manganese here. We have 3 manganese, so the manganese are balanced. And then we have to ensure that the charges are balanced, right? We have to count up the total charges on either side. So let's do that. How many charges total do we have on the left side? We have 5 times plus 3, so that's what? 15, right? And then we have minus 3 here, 3 times minus 1. So 15 minus 3 gives you what? Plus 12, right? Then we look on the reactants, the product side, the right side. We have 3 times plus 2, that's 6. And then 5, we have plus 6. And then 5 times minus 2, that's minus 10. And then we have 16, plus 16. So what does that give you? 6, 10 minus 6 gives you 4. Minus 4, 10 minus 6 gives minus 4. 60 minus 4 gives you what? Plus 12. So the charges are balanced, so therefore we can be confident that this is the correct balance equation for this reaction. All right? Any questions about this? Any questions? Any questions? Any questions? Any questions on the Zoom? All right, so let's do one more. Now this time, I'm not going to say anything. I'm just going to take what you tell me and write it here. So let me think of another one. Let me see. Suppose you're given suppose you're given S2O3 2 minus plus NO3 minus to give S4O6 2 minus plus N2. Again, this is just something I'm making up. I don't even know if this reaction will actually take place. So this is just purely for, you getting practice balancing these equations, right? So let me see. Okay, so I'm going to keep some water in my mouth so I'm not tempted to help you with this.
It's.
You would separate it into two equations, the NO3 minus into N2, and then the S2O3 2 minus to S4O6 2 minus. And then with the first equation, you would add three
It would be 2 and not 3.
that would make sense. Six. You put a two on the S2O3, that would balance it out, if the oxygen's not well, and they're both -2, so they're also. Oh, it would be -4 actually. So you would add 2 electrons to the S4O6. And then. That has a negative. Probably.
I'm so sorry, I just realized I made a mistake. Okay. Hold on, let me see it. Who did that? Hold on. Oh, no, it's okay. Okay, I thought that's something on the wrong side. Okay, go ahead. Let me not say anything more. Go ahead. Let me get some more.
You would add 6 water molecules to the N2. And then you would add 12 hydrogen to the, well, hydrogen plus,
Mhm.
and then 2NO3.
Mhm.
That makes, so that makes that a charge of 10. 10. So you would add 10 electrons to the side with the OH plus.
Mhm.
And you would multiply the Bobby equation by 5. So that would be 10 to
What's the next step?
you would add them, the
Okay.
2 equations together.
So you add them together and what will cancel out?
The 10 electrons.
Okay. Is there anything else that will cancel?
I don't think so.
Exactly, so just write on what's left. Plus 10 S2O3 minus to give N2. Plus 6H2O plus 5 S4O6 2 minus. So that should be the final answer, but again, check to make sure everything is balanced, including the charges on both sides. Let's start with the hydrogen. We have 12 hydrogens here. We have 6 times 2, 12 hydrogens. We have 2 nitrogens here. We have 2 nitrogens, so that's okay. In the case of sulfur, we have 10 times 2, 20. And here we have 5 times 4, 20 sulfur atoms. And then as far as the oxygens are concerned, we have 6 plus 30, right? So that's 36 oxygens on the left side. And here we have 6. And then we have 5 times 6, 30. So that's 36 oxygens on the right. And then now the charges. On the left side, we have plus 12, minus 2, minus 20. So what does that give?
-10.
Minus 10. And here we have minus 10. 5 times minus 2, minus 10. So everything is balanced, right? Okay. So that basically represents the end of chapter 4. So what I'm going to do now is post the assignment for chapter 4. So it's now published. And then I am going to create a Dropbox for the assignments. Assignment number 4. Let's see here. Oops. Okay, so I'm going to say that the deadline for submission of assignment number 4 be Friday, September 26th. Here. So that Dropbox will be available from today until 26th. Okay, so that is due on Friday, all right? So, as promised, I'm going to now move on to the next chapter, which deals with gases. And again, a lot of this will be review, all right? So again, I'll be going through it rather quickly. So we all know the difference between the different states of matter. You have solid, you have liquid, and you have gases. And gases are different from solids and liquids in that the particles, molecules, atoms, they're high energy, always moving. They move, the term that we use in terms of their motion, to describe your motion is translational, which means that they travel in straight lines unless they bump into each other or bump into the walls of the container, right? And as a result of that behavior at the microscopic level, that means that gases will have certain properties. For example, they tend to flow readily and they will totally occupy the entire container that they're in. And you might come across this term vapor from time to time. Vapor is basically in reference to a gas that is normally a liquid under room temperature conditions, all right? So therefore you hear the terms water vapor, methanol vapor, because water and methanol are normally liquids under current room temperature pressure. But when it comes to other gases like oxygen and hydrogen, they're considered to be gases because they exist as such under normal room temperature conditions. What you will find is that a lot of molecular compounds that are of a low molecular weight, they tend to be able to vaporize easily to form gases, all right? And this is just a list of different gases and their applications, all right? So let's talk about the theory that is used to explain the behavior of gases. It's called the kinetic molecular theory. And basically what this theory says is that the molecules are in rapid random motion, as we said before. Occasionally they'll collide with each other and collide with the walls of the container. And basically when they collide with the walls of the container, collectively, they would exert a pressure on the inside of the container, right? And I remember because I minored in physics when I was an undergrad, I remember there were some equations that was derived just to show you the relationship between the force exerted by the molecules and the total pressure exerted by the gas. Another aspect which is explained by the kinetic molecular theory is the fact that as you increase the temperature, the molecules become more energetic, right? And as a result, the average speed of the gas molecules would increase, all right? So this is all basically what the kinetic molecular theory is all about. So let's talk about a particular property of gases known as pressure. We need to define what this term pressure means. And again, this is something that I remember coming across in both chemistry and physics as a student. Pressure is the force per unit area, all right? So what that means is that if you apply pressure to an object over a particular area, then the pressure can be calculated as, write this down here. Come on. Okay, so pressure can be seen as equal to force divided by area, all right? So mathematically speaking, that's the relationship between pressure and force and area. Now, the units of pressure is dependent on the units that you use for force and the units that you use for area, right? And if you're talking about the SI system, the unit of force is newtons and the unit of area is meters per square, right? Meter squared, I should say. So therefore, the units of pressure will be newtons per meter squared, right? But there are other units that are used as well. There's one that is known as a Pascal unit. And you can have smaller units or larger units expressed using the prefixes in conjunction with that unit. So you can have kilopascal, which is actually most often used when it comes to expressing the pressure of a gas. And that's because the Pascal unit is relatively small. We're going to see the relationship between those units. Also, there's some other units, the atmosphere units and millimeter mercury units are also used as well when it comes to expressing pressure. All right. And this here gives you the relationships between the different units. So there's the atmosphere unit. So we set 1 atmosphere here, and that is equal to all of these right here. So 1 atmosphere is equal to 760 millimeter mercury. It's also equal to 760 torr. I'm going to explain later on, if not today, definitely by next class, how we arrive at these units, right? We have some other units here. To be perfectly honest, I don't anticipate us using this unit, this unit, this unit, or, well, these three, right? Bar, millibar, and pounds per square inch, right? We are going to encounter situations where newtons per meter squared is used. And by the way, newtons per meter squared is the same thing as the Pascal unit, as I said before. And then we have the kilopascal unit as well, right? So these are just basically different ways of expressing the units of pressure. Okay, so how do we measure pressure? Well, there are 2 instruments that I want to talk about. One is known as the barometer, which is used to measure atmospheric pressure, to measure the pressure exerted by the atmosphere. And I'm quite sure you're aware that the atmosphere is a mixture of gases, right? And gases exert pressure on anything that is submerged in it. So what we're talking about here is how do we measure the atmospheric pressure? Let me also say that the atmospheric pressure changes according to different weather conditions and so on. So this is where the atmosphere unit comes in, was defined by the pressure exerted by a column of mercury that is exactly 760 millimeters high, right? So therefore, based on that definition, 1 atmosphere is equal to 760 millimeters mercury. And also the millimeter mercury unit and the torr units are the same. The torr unit is named after an Italian physicist known as Torricelli, right? And it's also equal to this value expressed in kilopascal, right? So how do we measure the atmospheric pressure? Well, as I said before, the instrument is called a barometer. And you have different barometers of different levels of sophistication, but they operate on the same basis here. Now, to explain how this works, and this will be the last thing we're going to talk about. I'm just going to point to certain features between these 2 setups right here. So this setup here is a trough filled with mercury, right? And you have an open end tube right here. So basically, the mercury levels inside the tube would be equal to the mercury level outside. So they'll be at the same level. And that's because the atmospheric pressure acting on the surface here would be same as the atmospheric pressure acting through the tube onto the surface inside the mercury. So basically, they'll be at the same level as far as the open-ended tube is concerned. Now, the diagram on the right shows you a slightly different situation where you have a tube which is sealed at one end, right? So what they did is that they filled the tube with mercury, and I presume they're wearing gloves because you have to put your thumb on the open end, and then you invert it into the trough, right? And then you remove your thumb. And then what will happen is that if the tube is long enough, the mercury level will fall until it reaches about 760 millimeters mercury, right? And what that indicates is that this column of mercury is exerting a pressure at this point, right? Which is equally level at this point right here, which means that the mercury that is exerting the pressure here will be equal to the atmospheric pressure that is exerted on the surface outside of that column, all right? So that's where we get this whole idea of 1 atmosphere is equal to 760 millimeters of mercury, right? Okay, I'm gonna stop here for today and we'll continue our discussion of gas fees, all right? So I'll see you guys on Thursday, right? And for you guys out there in Zoom, I'm going to sign off right now.